Find the x-intercepts in the y-intercept if they exist of the function f of x equals x cubed minus x squared minus 11x plus 11 over x squared plus 4. So we're looking for the x-intercepts and the y-intercepts. I'm going to start with the y-intercept because it's always a little bit easier to work out. When you're finding a y-intercept, you're letting x equal 0, and that means substituting a 0 into the function. So f of 0 is 0 cubed minus 0 squared minus 11 times 0 plus 11 over 0 squared plus 4. That leaves 11 in the numerator and 4 in the denominator. So we have a y-intercept of 11 over 4. Then we want to find our x-intercept. To find an x-intercept, you let y equal 0. And this is written in function notation, and so f of x is used in place of y. So we're going to let f of x equal 0. That gives us the equation 0 equals x cubed minus x squared plus 11x plus 11 over x squared plus 4. Now this is a rational equation, and we're going to start by getting rid of the denominator, and we do that by multiplying both sides by that denominator. I multiply the right-hand side by x squared plus 4 and the left side by x squared plus 4. On the left side, 0 times anything is 0, so we get 0. And on the right side, we have canceled the denominator, and we're left with the expression that's in the numerator, x cubed minus x squared minus 11x plus 11. Now we want to solve this equation that is left, and we call this a polynomial equation. More specifically, it is a cubic because of the third power. Now to solve this, we are going to use a factoring technique called grouping. And I thought of this method because we have 4 terms, 1, 2, 3, 4 terms. And grouping is a method that typically works with 4 terms. Not every time, but it's a good thing to try when you have 4 terms. So this grouping method says to group 2 terms at a time together and factor the greatest common factor out of each group. So I'm going to group the first 2 terms together, and I'll group the second 2 terms together. And out of each of these groups, I'm going to factor the greatest common factor. The first group has a greatest common factor of x squared. And if I factor that out, I'll be left with x minus 1. In the second group, we have a leading negative term, so I'm going to factor a negative out. And I can also see that 11 is a common factor of each of those terms. So I will factor out a negative 11. If I factor out that negative 11, I have x minus 1 left inside the parentheses. Now at this step is when you'll know if the factor by grouping method will work. Because with factor by grouping, you need to have what's in the parentheses on both groups matching each other. So we do, so this method is working. So I'll factor out x minus 1 from this term, and if I factor out the x minus 1, x squared will be left inside the parentheses. And if I factor out from this term the x minus 1, minus 11 will be left inside the parentheses. Now I can use the zero product property and set each one of these factors equal to 0. X minus 1 equals 0, x squared minus 11 equals 0. And I'll solve this equation that's left. So I add 1 to both sides to get x equals 1. I'll add 11 to both sides to get x squared equals 11. And I can finish solving this by square rooting both sides. And that gives x equals plus and minus square root of 11. So this function has 3 x-intercepts, 1 square root of 11, and negative square root of 11. Find the x-intercepts and the y-intercept of the function. F of x equals x squared plus 3x minus 4. Let's start by finding the y-intercept. You can find a y-intercept by letting x equal 0. So we'll be substituting a 0 into the function. F of 0 equals 0 squared plus 3 times 0 minus 4. That simplifies to be negative 4. So we have a y-intercept at negative 4. Then we'll find the x-intercept. You find an x-intercept by letting y equal 0. In this example, we're using function notation. So instead of setting y equals 0, we'll set f of x equals 0. Setting f of x equals 0 would give us the equation 0 equals x squared plus 3x minus 4. And I'm going to try to solve this with factoring. The values in the front are need to multiply to be x squared. So that'll be x times x to get x squared. The terms in the back need to multiply to be 4. So the factors of 4 are 1 times 4 or 2 times 2, but I'm going to use 1 and 4 because I'm more likely to get the right middle number with 1 and 4. We're going to get 1 and 4, and we want the 4 to be positive and the 1 to be negative. We can check our factorization to make sure that we've done it right. X minus 1 times x plus 4 is x squared plus 4x minus x minus 4. We can combine the like terms in the middle. 4x minus x is 3x. And you can see that we do have the right factorization. Once you have it factored correctly, you will use the zero product property and set each factor equal to 0. X minus 1 equals 0, and x plus 4 equals 0. Solving these linear terms gives x equals 1 and x equals negative 4. So this function has 2 x-intercepts at negative 4 and positive 1. Write the equation in standard form for a circle with center, negative 3, 5, and tangent to the x-axis. So we're trying to write the equation of a circle. So let me write down what the standard form of a circle is first. The standard form of a circle is x minus h squared plus y minus k squared equals r squared. And that's where hk is the center of the circle and r is the radius. Now we are given the center of the circle to be negative 3, 5, so that means we know the values of h and k. So the only other value we need to know to find the standard form of a circle is the radius. And hopefully this other information about being tangent to the x-axis will be able to tell us what that radius is. So let's have an understanding of what it means for a circle to be tangent to the x-axis. And we'll do that with a picture. So here is the coordinate plane, and the horizontal line is the x-axis. If I were to draw a circle that is tangent to the x-axis, what that means is that the circle will touch the x-axis in a single point, rather than the circle crossing the x-axis or totally missing the x-axis. So this example here, let me change the color of it. This example here is a circle that is tangent to the x-axis. So what that does for us is it allows us to determine the value of the radius. If I start to draw this picture, I think it'll become more apparent to you. So for the example that we're working with, we have a center of -3, 5, and I know that the circle I want to draw is going to be tangent to the x-axis. And so that must mean that if I go down to the x-axis, this is the point that the circle is touching the axis at. And because of that, it's really easy to count how much we are, count the distance from the center to that point on the x-axis. So this ordered pair for the center is -3, 5, so that must mean that our radius is 5 for this particular circle. So we now know the radius of the circle is 5, and we can fill in h, k, and r into the standard form of the circle. So we have x minus -3 squared plus y minus 5 squared equals 5 squared. I'll simplify this double negative and simplify the squared, and that gives x plus 3 squared plus y minus 5 squared equals 25. So we have the standard form of a circle that has a center of -3, 5 and is tangent to the x-axis. Find the x-intercepts of the graph of the function without graphing the function. Our function is f of x equals square root of x plus 40 minus square root x minus 4. So we're looking for the x-intercepts, and you find an x-intercept by letting y equal 0. Our equation is written in function notation, so we're going to set f of x equal to 0 because that is y. So our equation is 0 equals square root of x plus 40 minus square root of x minus 4. So looking at this, we have a radical equation because we have a variable that is underneath a radical. The strategy for solving this type of equation is to isolate the radical and then square both sides to get rid of it. Now we have 2 radicals in our equation, so we're going to have to go through that process twice to get rid of both radicals. So I'm going to start by adding square root x to both sides. That gives square root x equals square root of x plus 40 minus 4. So I have one radical isolated on the left. This radical is a square root, so the way we get rid of a square root is to square both sides. I'll square the left, and to balance, I need to square the right as well. On the left-hand side, the square root and the square cancel each other out. And on the right-hand side, we're going to multiply this out. It becomes square root of x plus 40 minus 4 times square root of x plus 40 minus 4. When I multiply square root of x plus 40 times square root of x plus 40, that becomes x plus 40. Let me work that out on the side just so it makes a little bit more sense. I'm doing square root of x plus 40 times square root of x plus 40. And when we multiply radicals together, we multiply what's underneath them. So this becomes x plus 40 squared underneath the radical, and the square root and the square cancel each other out, and you get x plus 40. So it's a little bit messy with the variables, but you can see it very clearly happening with numbers. Square root of 2 times square root of 2 is square root of 4, and that's 2. So it always goes back to when you multiply these radicals that are the same together, it works out to be what's underneath the radical. So if I continue on, I'll multiply the outside two, and one of them has a radical and one doesn't. So I can't mix those, so I'll write it as minus 4 square root of x plus 40. And then I want to multiply the inside 2, and that's a minus 4 square root of x plus 40. And I want to multiply the last two together, and that's a minus 16, excuse me, a plus 16. And I still have x on the other side. I'm going to do a little bit of simplifying on the right-hand side. I can combine these radicals together, and I can also combine these constants together. So that would give me the equation x equals x plus 56, 40 plus 16 is 56, minus 8 square root of x plus 40. All right, so now we're in this part of the process where we have to repeat what we just did over again. We were able to isolate and get rid of one of the radicals, and now we still have another radical in our equation. So we now need to isolate this radical and square both sides to get rid of it. So I'm going to start isolating by subtracting x on both sides, and that gives me 0 on the left. I'll subtract 56. Negative 56 equals negative 8 square root of x plus 40. Divide by negative 8, and that gives 7 equals square root of x plus 40. Now that I've got that radical isolated, I'll square both sides. And that gives 49. The square root and the square cancel each other out, and I'm left with x plus 40, and I'll solve for x by subtracting 40 on both sides. And that gives me a solution of x equals 9. Now there's one more step that I need to take, and we have to do this step anytime we square both sides to try to find a solution. Most of the time, the step where you check your work or check your answer is an optional step that we're doing just to be careful. But whenever we square both sides, it's possible to get what we call extraneous solutions. So checking is actually part of the process when you solve radical equations where you square both sides. So I need to check to make sure that x equals 9 works in the original equation. So in the original equation where I'm starting to find the x-intercept, I'm going to substitute in an x equals 9. So that'll give 0 equals the square root of 9 plus 40 minus the square root of 9 minus 4. That's the square root of 49. The square root of 9 is 3. The square root of 49 is 7. And negative 3 minus 4 is negative 7. And 7 minus 7 is 0. So 9 is a solution to this equation, and that's also the x-intercept of this function. On this question, we want to find the x-intercepts and the y-intercepts of the function f of x equals 5x squared minus 2x minus 4. So let's start by finding the y-intercept. You can find a y-intercept by letting x equal 0, and that's substituting a 0 into the function. So f of 0 is 5 times 0 squared minus 2 times 0 minus 4, and that's negative 4. So this function has a y-intercept at negative 4. So let's find the x-intercept. To find an x-intercept, you let y equal 0. This is written in function notation, so we'll set f of x equal to 0 since f of x is y. So that gives the equation 0 equals 5x squared minus 2x minus 4. And with quadratic equations like this, I typically try to solve with factoring first. So I'll try factoring, but I have a feeling that this one doesn't factor. So we want the terms in the front to multiply to be 5x squared. And the only factors of 5 are 5 and 1. So I'm going to try 5x and x. The terms at the back need to multiply to be 4. And I have a couple of choices here. Factors of 4 are 4 times 1 or 2 times 2. So I'm going to try each one of these. Let's try 2 times 2 first. And the method I'm using for factoring is called the guess and check method or the trial and error method. So I'm trying this factor pair and I'm going to multiply it out to see if it works. So I'm going to multiply the inside two terms and the outside two terms because I've pretty much guaranteed that the first and the last term will be correct. So I'm only checking the middle. So that gives 2x and 10x, and if I were to combine those like terms together by adding, that would give me a 12x. By subtracting, it would give me an 8x, and neither one of those is the right middle term. So I know that this pair of 2 and 2 is not going to work. So let's try the other pair with 4 and 1. So I'll try 4 and 1 here. We're going to multiply the inside and the outside. That gives 4x and 5x. If I add those together, it gives me 9. If I subtract them, it gives me 1, and neither one of those are the right middle number. I could try switching the 4 and the 1 to make it a 4 and a 1 like this. And still, when I check this, inside and the outside, I get 1x and 20x. And if I add those, it gives me 21. If I subtract them, it gives me 19. And neither one of those is the right middle number. So I've exhausted every possibility for factoring this quadratic. So I know that factoring will not work to solve this quadratic equation. So instead of factoring, I'm going to use the method that is guaranteed to work every time when you're solving a quadratic equation, and that is using the quadratic formula. The quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And I'm going to use the values of a, b, and c in this formula. A is always the coefficient of the squared term. So for this example, a is 5. B is the coefficient of the x term. So b is -2. And c is the constant, which is -4. So I'll substitute these values into the formula. That's -2 plus or minus the square root of -2 squared minus 4 times 5 times -4. All of this over 2 times 5. Once I've got it substituted into the formula, I'm going to follow order of operations to simplify. I've got negative times negative, which is a positive. -2 squared is a 4. And 4 times 5 times 4, let's see what that is. Not sure I can do that in my head. 20 times 4, oh, that's 80. It'll be a plus 80 over 10. And 4 plus 80 would be 84 underneath that radical. And then I want to simplify the radical. And when you simplify a radical, you're looking for perfect square factors. So let's think about the factors of 84. That's 1 times 84, 2 times 41. No, that's not right. 21.
It would be 42.
Thank you very much. I was mixing up 2 and 4 there. 2 times 42. And 3 does go in there. Let's see, 3 goes into 84. 2, 28. Okay, I'm not seeing any perfect squares so far, but 4 is 1. See, 4 goes into 84 21 times. And 4 is a perfect square. So this is what I'm going to use to factor that 84. 4 times 21 over 10. The square root of 4 is 2, and the 21 stays inside the radical. And the last thing that we want to do is to reduce the fraction. You want to make sure that there are no common factors left in your fraction. So when I look at these 3 numbers, they're all even. So I know that 2 will divide into all 3 of them. 2 goes into 4 2 times, 2 goes into 2 once, and 2 goes into 10 5 times. So that gives 2 plus and minus square root of 21 over 5. And there is one more way that this can be written, and it's an either or, so you can type it this way, or you can type it as 2 separate fractions like this, 2 over 5 plus and minus square root of 21 over 5. On this question, we're given a graph, and we want to find the relative extrema. Specifically, the directions say, for what values of x does f obtain a relative minimum, and what are these relative minima? So looking at this graph, so we're starting with relative minimum. And we have a definition of relative minimum. And the definition says that we'll need to see a change in the function from decreasing to increasing. So it would be really helpful for us to identify where the relative extrema are if we identify the intervals of increasing and decreasing on this graph. So I'll do that with two different colors. So I'm going to start tracing the graph from left to right, and along this section right here we can see that the y values are increasing. And then we change to decreasing, and then it changes to increasing again. So I'm highlighting the increasing sections in yellow. And then let's get a new color. And we said it's decreasing along this section and decreasing along this section. We do have one interval where this function is constant, and that is here. The y values are unchanged along that section. So to find any relative minimums, we're looking for a change from decreasing to increasing. And you can see right here, to the left of this point, the graph is decreasing, and to the right, it is increasing. You can also identify it by the fact that we have a little dip in the graph. I like to call it a valley, and this will be a relative minimum. So that ordered pair is 0, -5. So we can say that this function has a relative minimum at, let me erase that, a relative minimum of -5, that's the y value, and it occurs at x equals 0. So this function has a relative minimum of -5 at x equals 0. And then we want to find relative maximum. And a relative maximum is going to occur when you have a change from increasing to decreasing. So you can see right here on the left of this point, the y values are increasing, and to the right of that point, they are decreasing. So that creates a relative maximum at this ordered pair. And it also happens right here. To the left of that point, the graph is increasing, and to the right, it is decreasing. So at that point 9, 2, we have a relative max. So this function has two relative maximums. So we have a relative max of that's a positive 3 at x equals -4. And we also have a relative max of 2 at x equals 9. For this question, we want to determine whether the relation represents a function. State the domain and the range of the relation. So typically with these type of problems, we're dealing with sets of ordered pairs. But this was presented to us in a table format. So in this first box, we have a list of items, and then we have arrows drawn to a second box. So this is showing us the correspondence between these two items. So we have here this first list. This will be our domain, and this one will be our range. So we're going to be able to say that the domain is Ottawa, Paris, Beijing, Libu, and Arica. Our range is Canada, France, China, and Chile. And then we want to decide whether this is a function. So we need to remember that the definition of a function is that every first coordinate corresponds to exactly one second coordinate. Every element in the domain corresponds to exactly one element in the range. And so we can go to each element in the domain and notice that it only has one arrow leaving from that element in the domain. So that means that every item in the domain is corresponding to one item in the range. So this is a function. In this question, we're given a graph, and we want to know for what value of x is g of x equal to 4. So with this question, we want to keep in mind that with function notation, g of x or f of x is the same thing as y. So our given information is that y is equal to 4. So if we look at our graph, and I'm going to highlight where we have y ordered pairs where the y is 4. And we notice that on the graph there's only one ordered pair where the y is 4, and that's going to occur at this x value of -7. So we can say that g of -7 is equal to 4, so the value of x is -7. On this example, we'd like to find the domain and range from the graph. And before we start finding that, I want to explain some of what we're looking at. So some of what we're looking at might seem a little bit unfamiliar, having these dashed lines written on the graph. What these dashed lines are, they're called asymptotes, and they are going to guide the pattern of where these arrows follow. So typically when we have an arrow, that means that the pattern continues. But in this example, that pattern that continues needs to be stopped at this value. In this case, it looks like at -3. So when we're looking at this graph, what we have to understand is that this graph will continue for the y to get larger and larger, but the x will be blocked by this dashed line here, this vertical asymptote. If we go to this arrow over here, it looks like the arrow is going down and to the left and down and to the left, and that pattern should continue. However, this dashed line is blocking it from going past this y value of 3. So we have to understand what those dashed lines are telling us as we look at this graph before we can determine what the domain and range are. So let me erase my markings. And when I find domain and range from a graph, I typically use a strategy where I will take a ruler, and if you don't have a ruler, you can use a pencil or a pen. And I like to start holding that ruler vertically. And when I'm holding the ruler vertically or pencil vertically, I am pointing to a spot on the X scale. So when I hold the ruler vertically, it's going to help me determine what the domain is. So I write the domain down in interval notation, and interval notation lists things from smallest to largest. So that's why I'm starting my ruler over here on the left-hand side, because this will be the smallest x value. My ruler is pointing to the smallest x value. And what I want to do is try to figure out when this graph begins so that I can think about when the domain begins. So I'm looking at this arrow here, And remember, this arrow is going to follow the pattern that we see in this picture. It will continue to go down and to the left, down and to the left, and that will continue on forever because that's what the arrow means. So because of that, there is no real beginning point for this graph, for this domain. So we're going to state that the domain is starting at negative infinity, meaning that that pattern will go on forever. So I've established when the domain starts. So I'm going to start moving my ruler to see when it stops. And as I'm moving my ruler to the left, I can see that my ruler is touching the graph. So that means that my domain hasn't stopped yet. And it's going to continue on. And continue on, and remember what we said this arrow over here means. So this arrow is meaning that the pattern is going to continue going up and to the right, but it will be blocked by this line here. It will never reach that line, and that means the domain is going to stop or take a break at that value. So we know the domain stops at this value of -3. After that point, we can see down here, we have another arrow. And this pattern means it's going to go down and to the left and down to the left as far as it can, but it is blocked by this line once again. And so immediately after I cross that point at -3, I am touching the graph again, which means my domain is starting again. So my domain will start again at -3. And it will continue until the same thing happens over here. We have another vertical asymptote at x equals 3. So we will have another stopping point in our domain at 3. And we'll have another starting point right after that line. It will go from 3. And it continues on. This arrow here means it goes on forever, moving down and to the right. And it will continue on till infinity. So then I want to find the range. With the range, we're going to hold our ruler horizontally because now holding it horizontally will point to the y scale. So once again, I'm at the bottom. Interval notation goes smallest to largest. And with the y scale, that's bottom to top. So these arrows that we see here will continue going down forever, so that means that our range will start at -infinity. I'll move up to try to see a stopping point for our graph and a stopping point for our range. And as I continue to move up, I can see that when I get to this point here, my y values stop, my graph stops. And so my range will stop at 0. And I'll put a bracket on that 0 to include 0 in the range. This point right here, 0, 0, is a point that's on the graph, and 0 should be included in the range. So beyond 0, this whole section in between 0, 0, and y equals 3, this line, there are no portions of the graph, so there are no y values along this section. But right after this line, you can see, right after this horizontal line, this dashed line, you can see the graph again in red. So I know the range starts again right here at this line. So the range will start again at 3. And this time you'll notice that I put a parenthesis on the 3. There is no ordered pair with a y value of 3 on this graph. This portion of the graph here gets closer and closer to y equals 3 but never reaches it. This portion here gets closer and closer to 3 but never reaches it. So since there is never a y value of 3 on this graph, we do not include it in the range. That's why I'm using a parenthesis. But beyond 3, above 3, all of these y values will be included in the range, and these arrows indicate that it goes on forever, and so we will end our range going to infinity. So we have, for the domain of this function, negative infinity to negative 3, union with negative 3 to 3, union with 3 to infinity. And for our range, that's negative infinity to 0, including 0, union with 3 to infinity. For this example, we have a center of a circle and a point on the circle, and we want to write the equation of the circle in standard form. So we're given that the center is 4, negative 5, and a point on the circle is negative 5, 1. And we want to write that standard form of a circle. The standard form of a circle is x minus h squared plus y minus k squared equals r squared. And we are given the center of the circle, so we already know h and k. In order to write this equation, we really only need to find r, the radius. We know the definition of the radius is the distance from the center to any point on the circle. And so if we're able to calculate the distance between these 2 points, we can find the radius. Now, there are a couple ways you can find the distance. There is a distance formula, but we can also use this standard form of a circle. You can use the center as this hk, and you can use xy as the point on the circle, and then solve for that radius. So I'll substitute those values in to get negative 5 minus 4 squared plus 1 minus negative 5 equals r squared, and I left off the squared there. This gives negative 9 squared plus 6 squared equals r squared. Negative 9 squared is 81, and 6 squared is 36. And 81 plus 36 would be 117. And if I square root both sides, I get that r is equal to 117. This does turn into a plus and minus, but the radius will be a distance, which is positive, so we use the positive one. And I apologize, we do need the square root on that, so square root of 117. So now we have the radius and the center, and we'll substitute these values in to write the standard form. So that would be x minus 4 squared plus y minus negative 5 squared equals square root of 117 squared. And I'll simplify this and this double negative, and our standard form is x minus 4 squared plus y plus 5 squared equals 117. Thank you for checking out my videos. Have a great day.